Okay. Yep. Okay. Great. I work at Tsinghua Daxue in the laboratory of Professor Tang Shuzhong, and others of us work there too. Okay. I'll have a couple of QR codes in the talk and some links. I've worked for Professor Tang for about 5 years. We work on two-dimensional materials. The most famous two-dimensional material is graphene, and we all use pencils, which traditionally have been made from graphite. The difference is graphite is layers of graphene, two-dimensional graphene, that just stick together by electrostatic forces. So we've all worked with two-dimensional materials and not really realized it because they're in the 3D form. Okay, and in fact, graphene was first made famous early in the 2000s, but before that we had buckyballs and carbon nanotubes. So this is actually the third allotrope, or third form of carbon that had sort of lower dimensionality, that has been supposed to have been the material of the future. And so hopefully we'll find that someday. The way graphene was first made, and the Nobel Prize was won, is using Scotch tape and graphite. And you simply pull it apart and apart and apart several times until it gets to be one molecule or one atom thick. And actually the Scotch tape dispenser is at a museum in Stockholm, where the Nobel Prize is given. So the other way to make graphene is by depositing atoms. And this is true for many two-dimensional materials. You deposit atoms on a surface, and that way you can control how it's made, on what surface it's made, the quality, and it's not contaminated with Scotch tape. There are many 2D materials in a honeycomb form. We call this a honeycomb form. Some of them also double up and make this sort of folded honeycomb form. Another type of 2D material that people study are TMDs, and I'm not going to pronounce this, and also MXenes. And these are 2 or 3 atom thick layers that become a two-dimensional material. Also, we have boron nitride, hexagonal boron nitride, where you have alternating atoms. And thick layers of silicon dioxide. So this is a 2D silicon dioxide. Excuse me. So two-dimensional materials have applications in high volume, in bulk. These can be used for catalysts, also for batteries. People are trying to put graphene into lithium batteries. In low volume, for example, just single layers on surfaces, these can be used for quantum computers, which there's one not so far from here, in electronics, photodetectors, and possibly even they will replace the source strain layer for transistors, basically, instead of FinFETs. So maybe in 5 or 10 years, you'll have electronics that use a 2D material for the source strain. These are studied in a number of ways. Chemically, for catalytic materials, electrical conductivity is studied, Raman, which is a shift in the wavelength of light, photoelectron or photoemission spectroscopy, electron diffraction, and scanning tunneling microscopy. I'll show you some of our data very briefly. This is a paper that came out last year. So you can see we're looking at a 2D material. We're looking at the photo emission. So a photon from the synchrotron comes in and electrons come out. We look at the spectra. Here we're looking at electron diffraction. These are diffraction spots from the 2D material on the surface. And we can fit these very accurately and learn about the properties of the material. We can also simulate these STM, or scanning tunneling microscopy images, to understand the crystal structure better. If you want to know more about STM, you can go back a couple of years and look at this PyCon talk. I think Shukai did it better than anybody else, so I would recommend you watch that. Very briefly, STM is done by scanning a tip across the surface and measuring conductivity and measuring a surface of constant conductivity. Here's a talk soon, it will be on YouTube, about electron diffraction. in our laboratory. This is a talk I gave a couple of years ago about electron diffraction. Okay, so some familiar forms of silicon. We know single crystal 3D. That's what we slice up to make wafers. But we also look at polysilicon, polycrystalline silicon for semiconductors, and various other materials, aluminum, copper, tungsten. These are all polycrystalline. Tinitride and various silicides. These are polycrystalline thin films used in semiconductor. And amorphous silicon used to be used, but not so much anymore. But the amorphous oxides are used for gate dielectrics. So when I talk about amorphous oxide, you guys know the difference between a quartz crystal and a pure SiO2 glass, right? One is glass, one is a crystal. Okay. So we can also see this in 2 dimensions. There's a 2-dimensional oxide layer, imaged, and also a 2-dimensional glass. So you see there's lots of rings, but there's no periodic structures, completely aperiodic. 2011, there was a Nobel Prize on quasicrystals. The discovery was a lot earlier than that. There was a lot of controversy, but they found 12-fold symmetry in electron diffraction. If you want to read about Penrose tiles, that will help you here. But this is what affected me very much in this study. Around 2023, these tiles, this is a mathematical thing. People discovered tiles or shapes that could be put together. It would never be repeating, no matter how far you tiled. Okay, and they discovered a single tile, just one shape, not a combination of shapes, but a single shape that could be tiled aperiodically forever. This was a lot of news. I recommend you read these articles. I'll show you a link to a video. About the same time in Germany, a quasicrystal was discovered on a surface. They made a 2-dimensional quasicrystal. And this was also a type of oxide. And this quasicrystal, this non-periodic, but almost periodic material produced in oxide could be mapped directly to a mathematical tiling that had been discovered just about 10 years earlier than that. So the early 2020s were a really hot year. So here's an example of an STM image of the quasicrystal and the mapping to the tiling that was recognized. And this is they worked very, very hard for 10 years and were able to determine the actual atomic structure of this quasicrystal and show how it maps to this mathematical tiling. If you want to learn more about Penrose tiles or about this monotile, I recommend these videos. So we have 3 types of materials. We have the aperiodic tilings, a tiling that never repeats. We have a quasicrystal, a 2D quasicrystal, which is similar to that, but not exactly the same thing. And third, something called a projection from higher dimensions. And I'll show you what I mean by that. Actually, it's going to take a minute here. Is it worth it? Probably is. Three, two, one. Here we go. So what this is this is a cut. You have a 5-dimensional crystal, periodic crystal in 5 dimensions, and you have a plane in an arbitrary direction. And as you tilt the plane through these 5-dimensional spaces, you get all kinds of different tilings, okay? And all of these are, most of them are non-repeating, non-periodic, aperiodic. Occasionally, if you happen to hit the right value, you get a rational number instead of irrational, you can get some periodicity. Anyway, this just gives you a quick idea of the mathematical aperiodic tiling. So I'll go back to this now. Okay. This is an STM snippet. This is a small piece of STM data that really got me interested, because after 2022-23 with the all the news about quasicrystals, this looked to me like a quasicrystal. So this got me really excited. Okay, and this comes from Professor Pai's lab at NTU, a collaborator of ours. And so let's see if we can look at some patches and hash them. So I found one pattern in the image and tried to build it up out of Gaussians. So I made this little tile, or this little kernel, as I call it, defined by bright spots and dark spots. You see the dark spots and bright spots here. And also determined an outline for the whole thing with unit Gaussians and defined which pixels would actually be used for the correlation. So we can take this pattern and break it down into just a vector with a couple of numbers. Here I use floats, but they could be single bytes, no problem. Okay, so we define these kernels, and then we correlate them with the image. You slide it across the image and compute this correlation integral, or correlation sum. And if you normalize it properly, you get a number between -1 and +1. And yes, once you've done this, once you've done a correlation at every single pixel, you look for the maxima. Okay, that's a pretty simple thing in Python. And so, for example, this is a map of the correlation integral. So this kernel is scanned across the whole image, and these peaks are where the correlation is maximum. Okay, so this looks a little like our raw data. I just drew a figure here so you can see what I'm talking about. Here's 7 maxima, and then there's the same maxima here, but I take the outline of the kernel and place it at the positions of the maxima. So, so far we see something happening. I don't know if it's a quasicrystal. I don't know if it's a crystal. I don't know if it's a glass. But we're taking steps to try to find that out by mapping the coordinates of these little kernels, or these little vectors, if you like. So for example, here's the raw data here. Okay, so we can see these are the triple spots, and these are all the double spots. The colors are for the different rotations. Here's a different shape. We have some piece of noise here, so we have too many spots here. So it's not a perfect correlation right now. We're getting a lot of noise. For example, you can see, I think this shape right here is not a good match. And also we completely missed, where is it? I missed it too. Oh, right there. So we should have found that one, we didn't. So this process is not perfect, but we're making progress on that. I said I'd talk about discrete cosine transform, but that's really not the right way to hash this image, since we know it's made of atoms, it's made of blobs. So can we make artificially, or make a library of vectors, or kernels as I call them, to do that? So I just started with totally random spots, limited the range of the brightness, gave them a minimum distance so we don't have two on top of each other, and then required them to have fixed bond length, a fixed distance between the two. None of these look really good. I think it's a good start, but we probably have to do more physical before we can make these vectors. So we probably need to restrict these to actually having bond angles that are physical, and maybe bond a number that's physical, 2 or 3 bonds. Or even use something like molecular dynamics to model the growth process. Okay. And so the next steps, yes, okay, I just said that, okay. So this would go in something, once you build a library of these kernels or vectors, these sets of numbers that define little patterns, that would go as, be used to try to make a human-independent model that fits the pattern with a reduced number of vectors until we can really see what's happening. I think I meant to show you this video. By the way, I just missed it before. This is just an example of how graphene grows, or how you would use molecular dynamics to build. This is not our data. This is just, again, from YouTube. But it gives you an idea of what's happening, how we get these rings of different shapes and sizes. And a simulation like this could build a library of structures without human intervention, without being biased, or without trying to find the patterns by hand. So that's on our list of things to do too. Okay. And finally, there we go. I'm just going to give you a couple of more videos here. We're talking about not convolutional autoencoders, but this is an excellent introduction to autoencoders, so it's worth it for the math. So what we're talking about is vector autoencoders, okay? Discrete vector autoencoders. And so these two videos explain better than I can what we need to do and what we need to learn to do, basically. So, and then yesterday I saw an excellent talk, and I'm really happy this was, I was really happy to sit into this one. I learned a lot about the machine learning and modeling, but I also learned about network X, and that's really important. This could be looked at as a network instead of as a bunch of atoms. Just look at the paths, the bright areas that follow from one atom to another. And perhaps cast as a network, it can be analyzed that way. And we can start finding a way to vectorize that instead. So that's it.
Thank you, David. So we have a Slido question.
Okay. Does anyone have a verbal question? Any humans? Or comments or help that someone can offer? Yeah, go ahead. You know, I cannot be, well, I'll try, but I just found out about it yesterday. So what I realized that there are tools to do that. I see. Well, look, the pattern itself was it's not into just little dots. All the dots are kind of connected to each other. Okay, they're rings. They're usually 5, 6, and 7 atom rings. And so they're in the physical reality, they're certainly all bonded together. They're all covalently bonded together. So it's easy from a physical point of view to imagine them as a network. Okay, like a molecule is covalent bonds. I guess so. Mm-hmm. Yes, so generate many small networks and look for them, look for matches. Or that's one way. The other way would be to just simply go little area by little area, identify a network and see if you start, and find a way to hash it, and then start seeing if you see repeated small networks. We're just trying to understand what this thing is. It's not random, it's not periodic, it's in between. And I need to know if it's just glass or if it's a quasi-crystal, if it has relationships and tiles that repeat over and over in different things. So be able to cast the pattern as a series of small networks that seem to repeat, not periodically, but repeat in different orientations. That would be the way I would use it. Yeah.
Any other question? David, as you can see, there's 2 questions in the slide.
Great.
Would you want to answer it?
Can I make this brighter?
Yeah.
There's a bright light in my eye.
Oh, okay. How is page hashing different from just eyeballing or use?
Well, okay. No, it's a good point. Yeah, I don't have my slides right here.
Yes,
so,
there's a slide. You don't want to?
I'm speaking.
Yeah.
Okay, so I don't have my slides available for you right now, but patch hashing, it's how you use it. Patch hashing is a way to find a representation in a small set of numbers, right? Now, I wouldn't use FFT, but I did talk about discrete cosine transform, which is the basis for JPEGs. It's a way to reduce a pattern into a small number of numbers or a small number of integers. But patch hashing allows you to express a pattern in a very small set of numbers so that you can start building histograms, like how many times do I get this? How many times do I get that? Classifying what, originally a small piece of image as a small set of numbers in 4, 5, 6, 8-dimensional space. And it allows you to start seeing repeated patterns by, having a higher count rate for certain hashes. Now, the hash doesn't have to be an exact match. You always have to reduce it because the image is too complicated, okay? So discrete cosine transform is one way to reduce it to a fixed number, depending on the space, the size of the space you transform it to, which is essentially the same as Fourier transform. And I don't know if that answers the question or not, but
Yeah, I think so.
okay.
Yeah, and that question is for a Python developer who want to try this. What is the first 3 steps?
Watch all the videos I recommend. I'm serious. I absolutely, really. And then go to tutorials. You find the tutorials that you like. You identify the person who speaks clearly to you. All kinds of tutorials out there. Most of them are just blah blah blah, or copied from each other. But you find the source of information that matches, that thinks the way you think, and follow those. Okay. And just, yeah, that's got to be it. YouTube tutorial. That's how I do things.
Okay.
Yeah.
Any question on site for David? Okay. If no, then thank you, David.
Okay. Thank you. And feel free. My email was in the first slide, so feel free to contact me, or feel free to come and work with us if you're interested in 2D materials. Thank you. Thank you.